Welcome back to History for Sleep, where we drift through the deep past one story at a time. Tonight we're going on a slow, soothing journey into one of the most profound mysteries our planet holds within its ancient bones. We're exploring a gap so vast, so inexplicable, that it makes the extinction of the dinosaurs seem like yesterday's news. This is the story of 1 billion missing years, a time hole in Earth's history that no one can fully explain, where the very rocks beneath our feet whisper of an erasure so complete that it challenges everything we thought we knew about how our world keeps its own memories. As always, I hope this video helps you drift off gently, or at least helps you put your worries into perspective by zooming out not just a few 100,000 years, but over 1 billion years into the deep, deep past. Of course, there's a small risk that it might be too interesting and keep you awake. But if that happens, well, at least you'll have learned something fascinating along the way, something that even the greatest minds in geology are still puzzling over as we speak. Before we float off into the past together, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this sleepy little channel grow, and it means the world to me to know that there are others out there who find comfort in these ancient mysteries. I'd also love to know where you're watching from and what time it is for you right now. Let me know in the comments. It's always such a joy to see our sleepy history community scattered gently across the globe, from midnight listeners in Tokyo to afternoon dreamers in London, all of us connected by our shared wonder at the vast story of our planet. Now, settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you like whispers on the wind, like the gentle erosion of time itself wearing away at the edges of consciousness. And as we begin this gentle voyage into the vast unknown, remember this video is for educational and relaxation purposes only and is not intended as medical advice. Ready? Let's begin our journey into the Great Unconformity, the most mysterious gap in Earth's entire geological record. Picture yourself standing at the rim of the Grand Canyon on a clear, starlit night. The moon casts silver shadows across the layered walls, each band of rock a page in Earth's autobiography, written in minerals and time. As your eyes trace down those magnificent walls, following the story backward through the ages, you're reading a book that spans nearly 2 billion years. The upper layers speak of ancient seas and deserts, of creatures that lived and died when the world was young. Each layer sits comfortably atop the one below it, a natural progression of time laid down like blankets on a bed. But then, if you know where to look, something extraordinary happens. There's a place where the story simply stops. This is where our mystery begins, in a seemingly innocent contact between two layers of rock. Above this invisible line, you have rocks that are roughly 550 million years old, filled with the first complex fossils, the strange and wonderful creatures of the Cambrian period. But directly below, touching these rocks as if no time has passed at all, lie stones that are 1.7 billion years old or even older. Between them, more than 1 billion years of Earth's history has simply vanished, erased as completely as if those years had never existed at all. This is the Great Unconformity, and it exists not just in the Grand Canyon, but in scattered locations across every continent on Earth. The discovery of this impossible gap began, as many great mysteries do, with confusion and disbelief. In the late 1800s, geologists exploring the American West were trying to make sense of the rock layers they encountered. They had developed a beautiful understanding of how sediments accumulate over time, how ancient seas deposit limestone, how rivers leave their sandy signatures, how volcanic eruptions interleave their ash between quieter periods. This science of stratigraphy was like learning to read Earth's language, and geologists had become quite fluent in it. They knew that in an undisturbed sequence, older rocks should always lie beneath younger ones, time stacked upon time in logical progression. John Wesley Powell, the one-armed Civil War veteran who led the first documented expedition through the Grand Canyon in 1869, was among the first to notice something deeply wrong with this picture. As his wooden boats carried him and his team through the canyon's heart, he observed the rock walls rising around him like the pages of an immense book. But this book, he realized, was missing entire chapters. Powell wrote in his journal about finding ancient crystalline rocks that looked as if they belonged to Earth's earliest epochs, yet sitting directly on top of them were much younger sedimentary layers, as if someone had torn out 1,000 pages from the middle of Earth's story. What Powell and his contemporaries were seeing was not just a local phenomenon. As geological surveys expanded across the globe throughout the late 19th and early 20th centuries, the same pattern emerged again and again. In Scotland's dramatic highlands, geologists found 800-million-year-old sandstones resting peacefully atop rocks that were 3 billion years old. In the heart of Africa, in Australia's ancient outback, in the shield rocks of Canada, the same impossible gap appeared. It was as if the entire planet had experienced some form of collective amnesia, forgetting 1 billion years of its own history. The human mind struggles to comprehend such vastness of missing time. 1 billion years is roughly a quarter of Earth's entire existence. To put this in perspective, imagine if human recorded history, from the first Sumerian writings to today, represents 1 second. At this scale, the missing time of the Great Unconformity would last nearly 4 months. 4 months of silence where there should be a continuous story. It's a gap so vast that entire mountain ranges could have risen to Himalayan heights and been worn down to nothing. Oceans could have opened and closed. The chemistry of the atmosphere could have changed completely, multiple times over. Life itself could have evolved in ways we can't imagine, leaving no trace of its experiments and dead ends. The rocks that border this gap tell us something profound happened, but they speak in riddles. The older rocks below the unconformity are often metamorphic or igneous, rocks that formed deep within Earth's crust under tremendous heat and pressure, or from the cooling of molten magma. They speak of a violent, active world of mountain building and volcanic fury. These basement rocks, as geologists call them, are the foundation stones of continents themselves, the ancient cores around which our modern lands assembled. When you run your hand across these ancient stones, you're touching materials that formed when Earth was truly young, when the planet was still figuring out how to be a world. The younger rocks above the unconformity tell a completely different story. These are sedimentary rocks, laid down grain by grain in ancient seas and rivers. They speak of a calmer world, one where erosion and deposition could proceed in measured rhythms. Most remarkably, these younger rocks often contain the first complex fossils, the earliest signs of animal life as we would recognize it. It's as if life waited for this mysterious event to pass before it could truly flourish, as if the Great Unconformity was not just a gap in the rock record, but a fundamental transition in Earth's ability to support complex organisms. The boundary itself between these two worlds is often remarkably smooth and flat, stretching for miles with barely any irregularity. This flatness is itself a mystery. Normally, when erosion wears away at rocks, it creates an uneven surface, following the different hardnesses of various rock types, cutting valleys and leaving hills. But the surface of the Great Unconformity in many places is almost impossibly level, as if the entire continent had been planned flat by some unimaginable force. Geologists call this a peneplain, an almost plane, and its existence speaks to erosion of a magnitude and consistency that challenges our understanding of how landscapes evolve. As we drift deeper into this mystery, consider what it means for a planet to lose its memory. Earth records its history in stone, each layer a diary entry written in minerals and fossils. Volcanic eruptions leave their ash layers like dated signatures. Ancient seas deposit their limestone memories. Rivers write their stories in sandstone. This rock record is how we know about the age of dinosaurs, about ancient ice ages, about times when the world was warm and swampy from pole to pole. But for this billion-year gap, the diary pages have been torn out, burned, or were never written at all. The traditional explanation that geology textbooks offered for decades was elegantly simple: erosion. The story went that the ancient basement rocks were once mountains, and over vast spans of time they were worn down by wind and rain until they formed a flat surface, upon which younger sediments were eventually deposited. This explanation has a beautiful logic to it, and erosion certainly played a role. But as our understanding has deepened, we've realized that simple erosion cannot account for the global nature of this phenomenon, nor for its timing, nor for its remarkable completeness. Think about erosion as we see it today. Yes, mountains wear down, but it's a patchy, uneven process. The Appalachians have been eroding for 300 million years, yet they're still there, still mountains, albeit lower and rounder than they once were. The Scottish Highlands have endured 500 million years of erosion and remain rugged and dramatic. For the Great Unconformity to exist as it does, erosion would have had to operate on a scale and with a thoroughness unlike anything we see in the modern world. It would have been erosion as a global catastrophe, or perhaps erosion operating under rules entirely different from those we understand today. Some geologists in the early 20th century proposed that the Great Unconformity represented not one event but many, that perhaps different parts of the world lost their records at different times, and only by coincidence do these gaps appear to align. But as dating techniques improved, particularly with the advent of radiometric dating in the mid-20th century, it became clear that the timing of the unconformity, while not perfectly simultaneous worldwide, clusters around the same general period in Earth's history, roughly 550 to 800 million years ago, depending on location. This clustering suggests that something global was indeed happening, something that affected the entire planet's ability to preserve its geological record. The mystery deepened further when geologists began to study the microscopic details of the rocks at the boundary. Using electron microscopes and chemical analysis, they found evidence of extreme chemical weathering in some locations, the kind of weathering that occurs when rocks are exposed to acidic conditions for extended periods. In other places, they found rounded pebbles and sand grains that speak of long transport by water or ice. Some locations show evidence of ancient soil horizons, suggesting that the basement rocks were exposed at Earth's surface for millions of years before being buried again. Each clue adds another piece to the puzzle, but the complete picture remains frustratingly elusive. As we contemplate this vast missing time, it's worth reflecting on what was happening to life during this period, or rather what we think might have been happening, because the biological record is almost as mysterious as the geological one. Before the Great Unconformity, life on Earth was entirely microscopic, dominated by bacteria and archaea, with perhaps some early eukaryotes, cells with nuclei, beginning to experiment with complexity. These organisms left few fossils, mostly just chemical signatures and occasional preserved mats of bacteria, called stromatolites. They lived in a world with very little oxygen in the atmosphere, under a sun that was significantly dimmer than today's, on a planet that may have been entirely unfamiliar in its climate and chemistry. After the Great Unconformity, in the geological blink of an eye, life exploded into complexity. The Cambrian explosion, beginning around 541 million years ago, saw the sudden appearance of most major animal body plans: trilobites with their compound eyes, early vertebrates with their nascent backbones, weird and wonderful creatures like Anomalocaris and Hallucigenia that seem like they belong in science fiction rather than science fact. It's as if life had been holding its breath during the missing billion years, waiting for something to change, and when that something finally happened, evolution went into overdrive. This temporal correlation between the Great Unconformity and the Cambrian explosion has led many scientists to wonder if the two events are connected. Did whatever caused the loss of 1 billion years of rock record also set the stage for animal life to flourish? Was the erasure of geological memory somehow necessary for biological complexity to emerge? These questions take us to the edge of what science can currently answer, into realms where hypothesis and speculation blend with wonder and imagination. One intriguing observation is that the Great Unconformity seems to coincide with major changes in ocean chemistry. The oceans after the Unconformity show evidence of being more oxygenated, with different ratios of isotopes that suggest fundamental changes in how carbon and other elements cycle through Earth systems. Some scientists propose that the erosion associated with the Unconformity delivered massive amounts of nutrients to the oceans, fertilizing them and allowing photosynthetic organisms to proliferate, pumping oxygen into the atmosphere and setting the stage for animal life. In this view, the Great Unconformity was not just a destroyer of rock records, but a creator of new possibilities for life. As we move deeper into our exploration, consider the detective work involved in studying something that, by definition, is not there. How do you investigate an absence? How do you study a gap? Geologists have had to become creative, looking not just at what remains, but at what should be there and isn't. They study the rare locations where some rocks from the missing time period have survived, islands of preservation in an ocean of absence. They use computer models to simulate what Earth's surface might have looked like during different scenarios. They examine the chemistry of ancient oceans preserved in limestone and other marine rocks. Each approach offers a different window into the mystery, though none yet provides a complete view. The modern study of the Great Unconformity employs tools that would have seemed like magic to Powell and his contemporaries. Mass spectrometers can measure the ratios of different isotopes in rocks, revealing the temperatures at which they formed and the sources of their materials. Electron microscopes can image individual mineral grains, showing their history of growth and dissolution. Supercomputers can model the movement of continents and the evolution of climate over billions of years. Satellites can map the extent of unconformities across entire continents. Yet despite all this technological prowess, the fundamental mystery remains unsolved. There's something deeply humbling about the Great Unconformity. Here we are, a species that has walked on the moon, that has sent robots to Mars, that has decoded the human genome and detected gravitational waves from colliding black holes, and yet we cannot fully explain a gap in our own planet's history. It reminds us that Earth still holds profound secrets, that our homeworld is in many ways still alien to us, still capable of surprising us with mysteries that challenge our most basic assumptions about how planets work and how time leaves its marks. As you drift towards sleep, let your mind wander through this missing billion years. What wonders might have existed that left no trace? What experiments in life might have flourished and failed? What mountains rose and fell? What oceans opened and closed? What climates came and went, all erased from the record as completely as a dream fades upon waking? The Great Unconformity invites us to embrace uncertainty, to find peace in mystery, to accept that some questions may never have complete answers. The rocks below the Unconformity, those ancient basement stones, are among the oldest things you can touch on Earth's surface. They formed when our planet was young and violent, when the moon loomed larger in the sky, when days were shorter because Earth spun faster, when no oxygen sweetened the air and no ozone layer protected the surface from the sun's harsh radiation. These rocks witnessed Earth's youth, and then they witnessed something so profound that it erased 1 billion years of subsequent history. What they witnessed, they cannot tell us directly, speaking only in the cryptic language of minerals and chemistry. The rocks above the Unconformity tell of a different world entirely, a world preparing for the explosion of complex life, a world with oxygen beginning to accumulate in the atmosphere, with oceans taking on their modern chemistry, with continents perhaps arranged in configurations that would soon enable the flourishing of biodiversity. These younger rocks speak of potential realized, of life taking its first tentative steps toward complexity, of Earth becoming the living world we know today. Between these two worlds lies the silence of the Great Unconformity, a silence that speaks volumes about the nature of time and memory on geological scales. It reminds us that Earth's history is not a complete record but a fragmentary one, full of gaps and mysteries. What we know about our planet's past is built from the pieces that survived, the fragments that escaped whatever great erasure created the unconformity. We are readers of an incomplete book, archaeologists of time working with partial evidence, detectives investigating a crime scene where most of the evidence has been destroyed. As we prepare to move into our next chapter, to explore the world that existed before this great gap, remember that we are embarking on an exercise in imagination, informed by science. We will piece together the fragments that remain, the whispers of evidence that survived the great erasure, to paint a picture of Earth before the unconformity. It will be a world alien yet familiar, a world that held the seeds of everything that would come after, yet a world that was fundamentally different from anything in our experience. The story of Rodinia, the supercontinent that dominated Earth before the Great Unconformity, is a story written in fragments of ancient crust, in the alignment of magnetic minerals, in the matching of rock types across modern ocean basins. It's a story of a world where all land was one land, where the entire solid surface of Earth was gathered into a single immense continent surrounded by an even more immense ocean. This was a world of extremes, of vast deserts in continental interiors and endless coastlines, where the single ocean met the single land. Rodinia's very existence was unknown until the late 20th century, when geologists began to piece together evidence from around the world. The name itself means motherland in Russian, chosen by the scientists who first proposed its existence. They noticed that rocks of similar age and type, dating to about 1.3 to 900 million years ago, could be found on different modern continents. When these continents were mentally reassembled like pieces of a giant jigsaw puzzle, moving them back through time using the evidence of seafloor spreading and continental drift, they seemed to fit together into a single landmass. The assembly of Rodinia was a slow-motion collision lasting hundreds of millions of years. Smaller continental blocks, the broken pieces of even earlier supercontinents, drifted across the globe and gradually collided, their collisions raising mountain ranges that would have dwarfed the modern Himalayas. These mountains, now eroded to their roots, can still be traced as bands of highly deformed and metamorphosed rocks running through the hearts of modern continents. The Grenville Mountains of eastern North America, now reduced to gentle hills, were once as mighty as any mountains Earth has ever seen, raised when Proto-North America collided with other continental blocks to form part of Rodinia. Life in the age of Rodinia was humble by modern standards, but revolutionary for its time. The oceans were dominated by microscopic organisms, bacteria and archaea that had already been evolving for over 2 billion years. But something new was stirring in these ancient seas. Eukaryotic cells, cells with nuclei and internal compartments, were becoming more complex and diverse. Some of these early eukaryotes had learned to photosynthesize, having absorbed photosynthetic bacteria that became chloroplasts. Others had developed the ability to eat other cells, engulfing their prey in a process that would eventually lead to predation on a larger scale. The first multicellular life may have appeared during Rodinia's reign, though the evidence is frustratingly sparse. Mysterious fossils called Gripenia, spiral forms up to several centimeters long, date back to this period and might represent early algae or other multicellular organisms. Even more mysterious are the rare impressions of what might be early multicellular animals, though most scientists remain skeptical, as these fossils are poorly preserved and difficult to interpret. What is clear is that life was experimenting with new forms and new ways of living, setting the stage for the explosion of complexity that would come after the Great Unconformity. the climate of Rodinia's world was unlike anything in human experience. With all land gathered into one mass, the interior of the supercontinent would have been a vast desert, possibly the largest desert Earth has ever seen. Rainfall would have been restricted to the coasts, unable to penetrate far into the continental interior. Summer temperatures in the heart of Rodinia might have exceeded anything seen on Earth today, while winters could have been bitterly cold, with no moderating ocean influence. This extreme continentality would have created powerful monsoons along the coasts, with seasonal reversals of wind patterns, driving intense rainfall during parts of the year and severe drought during others. The ocean surrounding Rodinia, called Morovia, was similarly extreme. Covering perhaps 90% of Earth's surface, it was an ocean beyond imagination, with waves that could travel halfway around the planet without encountering land. The chemistry of this ocean was different from modern seas, with less oxygen and different ratios of dissolved salts. Iron could still exist in dissolved form in these waters, something impossible in today's oxygenated oceans. When this dissolved iron occasionally oxidized, it would precipitate out as bands of iron oxide, creating the banded iron formations that we can still see in rocks from this period. But Rodinia was not destined to last. Beginning around 850 million years ago, the supercontinent began to break apart, torn by rising plumes of hot mantle, material that stretched and thinned the continental crust. This breakup was not a simple splitting, but a complex fragmentation, with different pieces pulling apart at different times and in different directions. Volcanic eruptions would have been common as molten rock exploited the cracks in the fragmenting continent. New ocean basins opened as the fragments drifted apart, and the global geography began to reorganize itself into something entirely new. It was during this breakup, or shortly after, that the Great Unconformity began to form. The relationship between Rodinia's fragmentation and the missing billion years of rock record is still debated, but many geologists see a connection. The breakup of a supercontinent is a time of tremendous geological upheaval, with extensive volcanism, rapid changes in sea level, and dramatic shifts in climate. These changes could have created conditions favourable for extensive erosion, though whether they alone can explain the global nature of the Great Unconformity remains uncertain. As Rodinia broke apart, the fragments that would become our modern continents began their long journeys across the globe. What is now Australia rifted away from Western North America. South China separated from Madagascar. Smaller fragments that would eventually become parts of Europe and Asia began their independent wanderings. Each fragment carried with it a piece of Rodinia's history, locked in its oldest rocks, waiting for future geologists to decipher. The breakup of Rodinia may have triggered one of the most dramatic climate changes in Earth's history. As the supercontinent fragmented, more coastline was created, and more of the land surface was exposed to moisture-bearing winds from the ocean. This increased rainfall would have accelerated chemical weathering of rocks, pulling carbon dioxide from the atmosphere as minerals broke down. With less CO2 in the atmosphere, the planet would have cooled, possibly triggering the ice ages that some scientists believe are connected to the Great Unconformity. There's a poetic symmetry to the idea that the breakup of a supercontinent might have erased much of the geological record of that supercontinent's existence. Rodinia's fragmentation may have destroyed the evidence of Rodinia itself, like a book that, in falling apart, somehow erases its own pages. The very forces that created our modern world geography may have also created the greatest gap in our planet's recorded history. As we stand on the edge of the Great Unconformity, looking back at the world of Rodinia, we're looking at a planet that was both our Earth and not our Earth. The same physical laws applied, the same chemical reactions occurred, the same sun shone in the sky, though it was dimmer then. Yet the configuration of continents, the chemistry of the oceans, the composition of the atmosphere and the nature of life were all fundamentally different. It was an alien world that was also our world, a past so distant that it challenges our ability to imagine it, yet a past that set the stage for everything that would follow. The transition from the world of Rodinia to the world after the Great Unconformity was not just a change in rock types or continental positions. It was a fundamental transformation of Earth as a planet. The Earth that emerged from the missing billion years was a planet ready for complex life, with oxygenated oceans, modern-style plate tectonics, and a climate system capable of supporting the diversity of life that would soon explode across the globe. Something happened during that missing time, something profound and transformative, something that prepared our planet for the next chapter in its story. And what a chapter it would be. The Cambrian explosion, beginning around 541 million years ago, just after the Great Unconformity, represents one of the most spectacular events in the history of life. In a geological instant, perhaps just 20 million years, most of the major animal body plans that exist today appeared in the fossil record. Eyes evolved, allowing organisms to see their world for the first time. Shells and hard parts developed, providing protection, but also ensuring better preservation as fossils. Predation became a driving force in evolution, spurring an arms race between hunters and prey that continues to this day. The Cambrian seas were filled with creatures that seem almost impossibly strange to modern eyes. Opabinia, with its 5 eyes and forward-facing grasping arm. Wiwaxia, covered in scales and spines like some medieval armour. Morella, looking like a cross between a shrimp and a trilobite. And dominating them all, at least in size, was Anomalocurus, a predator up to 2 meters long with grasping arms and a circular mouth lined with sharp plates. These were the pioneers of animal life, the first experiments in being large, complex and mobile. But perhaps the most significant creatures of the Cambrian were also some of the smallest and least impressive looking. Pikaia, a tiny worm-like creature no longer than your thumb, possessed something revolutionary, a notochord, a flexible rod running along its back that was the precursor to the vertebrate backbone. This humble creature, or something very much like it, was the ancestor of all vertebrates, including fish, amphibians, reptiles, birds, mammals, and ultimately us. Every human being carries within their spine the legacy of these first Cambrian chordates. The Cambrian world was not just about animals. The seafloor was covered with microbial mats, as it had been for billions of years, but now these mats were being disrupted by burrowing animals, churning the sediment in search of food. This bioturbation, as scientists call it, fundamentally changed how nutrients cycled through the ocean system. The clear waters that had characterized Earth's seas for billions of years became murky with suspended sediment. The simple, stratified ecosystems of the Armdams of Precambrian gave way to complex three-dimensional communities with organisms living at all levels from the seafloor to the water's surface. On land, the Cambrian world remained largely barren, though not lifeless. Bacterial mats probably covered moist surfaces, and simple fungi may have begun their colonization of terrestrial environments. But there were no plants as we know them, no insects, no animals of any kind above the high tide line. The continents were bare rock and sand, sculpted by wind and rain, but not clothed in green. Rivers ran clear, carrying sediment to the sea, but not the organic matter that colours modern rivers brown. It was a world waiting for life to make the leap from sea to land, a leap that would not come for another 100 million years. The rocks that tell us about the Cambrian explosion sit directly on top of the Great Unconformity in many locations around the world. The contrast could not be more stark. Below, crystalline basement rocks speaking of deep crustal processes, mostly barren of fossils, recording a world of simple, microscopic life. Above, sedimentary rocks packed with shells and tracks and burrows, recording a world suddenly teeming with complex animals. The boundary between them represents not just missing time, but a fundamental transformation in the nature of life on Earth. One of the most famous locations where this transition can be observed is in the Burgess Shale of British Columbia. Here, In rocks about 508 million years old, conditions were perfect for preserving not just shells and hard parts, but also soft tissues. The fossils of the Burgess Shale provide our clearest window into Cambrian life, showing us creatures in exquisite detail, sometimes even preserving their last meals in their guts. These rocks sit not directly on the Great Unconformity, but not far above it in geological terms, close enough that they record a world still reverberating from whatever caused the Great Erasure. The question of what triggered the Cambrian explosion has occupied scientists for over a century. Charles Darwin himself worried about it, seeing the sudden appearance of complex animals as a potential challenge to his theory of gradual evolution. We now know that animal life didn't appear from nothing. Genetic evidence tells us that the major animal groups had been diverging from common ancestors for perhaps 100 million years before they appear in the fossil record. But something allowed them to suddenly become large, complex, and preserved as fossils all at about the same time. Many scientists see a connection between the Great Unconformity and the Cambrian explosion. The massive erosion that created the unconformity would have delivered enormous amounts of nutrients to the oceans, particularly phosphorus, which is essential for life but often in short supply in marine environments. This nutrient pulse could have fertilized the oceans, allowing photosynthetic organisms to proliferate and produce more oxygen, creating conditions favorable for large active animals. The erosion would also have delivered calcium and other minerals necessary for building shells and skeletons, providing animals with the raw materials for hard parts. Another possible connection involves the changes in ocean chemistry that occurred around this time. The oceans after the Great Unconformity show evidence of being more oxygenated and having different pH levels than earlier oceans. These chemical changes might have crossed critical thresholds that allowed animals to build shells and grow to larger sizes. The evolution of eyes, which seems to have happened multiple times independently during the Cambrian, might have been triggered by changes in ocean clarity or light penetration. Once some animals could see, the evolutionary pressure to develop better vision, or to hide from those with vision, would have been intense. The climate system that emerged after the Great Unconformity was also different from what came before. The breakup of Rodinia had created a world with more continental margins, more shallow seas, and more diverse environments than had existed during the supercontinent's reign. This geographic diversity translated into ecological diversity, providing numerous niches for life to explore and exploit. The arrangement of continents also affected ocean currents and atmospheric circulation, creating a more complex and varied climate system that could support a greater diversity of life. As we contemplate this transition from the missing time to the explosion of life, we're witnessing one of the most profound transformations in Earth's history. A planet that had been dominated by microbes for 3 billion years suddenly became a planet of animals. The strategies that had worked for billions of years, being small, simple, and reproducing quickly, were supplemented by new strategies, being large, complex, and competing through behavior and morphology rather than just biochemistry. It was a revolution as significant as any in Earth's history, and it happened in the shadow of the Great Unconformity. The preservation of this story in stone is itself remarkable. The soft-bodied creatures of the Precambrian left few fossils, their bodies decaying completely or leaving only the faintest impressions. But the hard-shelled animals of the Cambrian left abundant fossils, their shells and carapaces resistant to decay. This difference in preservation potential means that the contrast across the Great Unconformity appears even more dramatic than it actually was. Life didn't appear suddenly. It suddenly became visible to us, future observers trying to read the story in stone. There's something deeply moving about standing at an exposure of the Great Unconformity, placing your hand on that boundary between two worlds. Your palm might rest on rocks that formed when Earth was young and lifeless, your fingers touching rocks that record the dawn of animal life. Between them, invisible but profound, lies a gap of 1 billion years, a third of our planet's history compressed into a line thinner than paper. It's a humbling reminder of the vastness of geological time and the fragmentary nature of our planet's memory. As geologists, we often speak of reading the rocks, but at the Great Unconformity, we're faced with pages that are missing, a story interrupted. We must become not just readers but detectives, piecing together clues from what remains to imagine what was lost. Every fragment of rock that survived from the missing time is precious, a messenger from a lost world. Every chemical signature, every isotope ratio, every mineral grain tells part of the story, though the full narrative remains elusive. The scientific effort to understand the Great Unconformity has intensified in recent years, driven by new technologies and new ideas. Researchers have used sophisticated dating techniques to pin down exactly when the unconformity formed in different locations. They've analysed the chemistry of zircon crystals, nearly indestructible minerals that can survive even the most intense erosion, to understand what was happening to Earth's crust during the missing time. They've created computer models of global climate and erosion to test different scenarios for how such complete erosion could have occurred. One of the most intriguing recent discoveries is that the Great Unconformity might not be as uniform as once thought. Detailed studies have shown that in some locations, the gap in time is larger than in others. In some places, thin layers of rock from the missing interval have been preserved, offering precious glimpses into this lost period. These variations suggest that whatever caused the Great Unconformity didn't affect the entire planet equally, that there were refugia where normal geological processes continued even as most of the planet's surface was being erased. These surviving fragments from the missing time are like islands of memory in a sea of forgetfulness. They tell us that life continued evolving during the gap, that mountains were still being built and eroded, that volcanoes were still erupting, that all the normal processes of a living planet continued even as their record was being destroyed elsewhere. The missing billion years were not a pause in Earth's history, but a chapter written in disappearing ink, visible only in scattered fragments and indirect evidence. The study of these fragments has revealed tantalizing hints about what was happening during the missing time. Some show evidence of extensive glaciation, supporting the idea that massive ice sheets might have been responsible for the erosion. Others show signs of intense chemical weathering, suggesting that unusual atmospheric or oceanic conditions might have accelerated the breakdown of rocks. Still, others preserve evidence of life, including possible early animals, though these fossils are controversial and their interpretation disputed. As we near the end of this first part of our journey through the Great Unconformity, it's worth reflecting on what this mystery means for our understanding of Earth and our place on it. We live on a planet that can erase its own history, that can undergo transformations so complete that they leave barely a trace. The solid ground beneath our feet, which seems so permanent and unchanging, is actually dynamic and ephemeral on geological timescales. Mountains that seem eternal are temporary wrinkles on Earth's surface. Continents that seem fixed are actually drifting across the globe. And the rock record that we rely on to understand our planet's past is incomplete, with gaps that may hide wonders we can barely imagine. The Great Unconformity also reminds us of the power of time. Given enough time, even the seemingly impossible becomes inevitable. Continents collide and split apart. Oceans open and close. The chemistry of the atmosphere changes completely. Life evolves from simple to complex, from microscopic to macroscopic, from water to land to air. And sometimes, given enough time, 1 billion years of history can be erased, leaving only the faintest traces of what once was. Yet despite this erasure, despite the missing 1 billion years, life found a way not just to survive but to flourish. The Cambrian explosion that followed the Great Unconformity was not a recovery, but a revolution. Not a return to what was but an advance to something entirely new. In this sense, the Great Unconformity was not just an ending but a beginning. Not just a destruction, but a creation. It cleared the stage for the next act in life's drama, an act that would eventually lead to us sitting here, contemplating the mystery of our planet's missing memory. As you drift towards sleep, let your mind wander through these deep corridors of time. Picture the ancient world of Rodinia with its vast deserts and endless ocean. Imagine the slow breakup of the supercontinent, the opening of new seas, the changing of the climate. Think about the mysterious forces that erased 1 billion years of history, leaving only whispers and fragments, and contemplate the explosion of life that followed, the sudden appearance of eyes and shells, and all the complexity that would eventually lead to consciousness itself contemplating its own origins. We've explored the what and the when of the Great Unconformity, but the why remains elusive. In our next chapter, we'll dive deeper into the theories that scientists have proposed to explain this massive erasure. We'll explore the idea of a Snowball Earth, a planet frozen from pole to pole, its ice sheets grinding away the rock record. We'll consider the possibility of unusual erosion during the assembly and breakup of supercontinents. We'll examine the chemical evidence locked in ancient minerals and the stories they tell about a world very different from our own. The mystery of the Great Unconformity is far from solved, and perhaps that's part of its appeal. In an age where it seems like science has explained everything, here's a reminder that our planet still holds profound secrets. The Earth beneath our feet is not fully known to us, its history not completely recorded, its past not entirely accessible. There are gaps in our knowledge as vast as the gaps in the rock record, mysteries as deep as time itself, but science is patient and persistent and clever. Each year brings new discoveries, new techniques, new ideas about what might have happened during Earth's missing billion years. Perhaps one day we'll understand exactly what caused the Great Unconformity, what forces could erase 1 billion years of planetary history. Or perhaps it will remain a mystery, a reminder of the limits of our knowledge and the vastness of deep time. Either way, it stands as one of the most profound puzzles in Earth's history, a gap that makes us wonder what other secrets our planet might be hiding. The rocks are patient teachers, waiting millions or billions of years for someone to come along and read their stories. The Great Unconformity is perhaps their greatest lesson, teaching us about the power of time, the impermanence of even the most solid-seeming things, and the resilience of life in the face of planetary transformation. It's a lesson written not in words but in minerals and gaps, in presence and absence, in what remains and what has been lost. As we prepare to continue our journey in the next part, exploring the specific theories about what caused this great erasure, remember that we're not just investigating a geological mystery, we're exploring the deep history of our home, the planet that gave birth to us and every living thing we've ever known. The Great Unconformity is part of our story, even if we don't fully understand it. The missing billion years are our missing years, a gap in our planetary family history that we're still trying to fill. The ancient rocks below the Unconformity knew a younger Earth, a different Earth, an Earth we can barely imagine. The younger rocks above knew an Earth preparing for the explosion of complex life, an Earth becoming more like the world we know. And between them, in that knife-edge boundary that represents 1 billion missing years, lies one of the greatest mysteries our planet has to offer. It's a mystery that invites us to think in geological time, to imagine processes operating over scales that dwarf human experience, to accept that some questions may take generations to answer, if they can be answered at all. Part 2. Echoes of a Lost World. As we drift deeper into the mystery of Earth's missing billion years, we turn our attention now to the theories that scientists have proposed to explain this vast erasure. Each theory is like a story told by the rocks themselves, whispered across the eons, waiting for us to develop the tools and understanding to hear them properly. The first and perhaps most dramatic of these theories takes us into a world so alien, so completely transformed from anything in human experience, that it challenges our very conception of what Earth can be. This is the story of Snowball Earth, a time when our planet may have been frozen from pole to equator, encased in ice like a cosmic marble spinning through the darkness of space. The idea of a completely frozen Earth was so radical when first proposed that it was dismissed by many scientists as impossible. How could the entire planet freeze over? And more puzzling still, if it did freeze, how could it ever thaw again? Ice reflects sunlight back into space, so a frozen Earth should stay frozen forever, locked in what physicists call a runaway ice albedo feedback. Yet the evidence began to accumulate, written in rocks from every continent, telling a story that seemed impossible, yet increasingly undeniable. The rocks spoke of glaciers at sea level in the tropics, of ice-rafted debris in equatorial oceans, of a world transformed into something that barely seems like Earth at all. The journey toward understanding Snowball Earth began in the 1960s, when geologist Brian Harland was studying ancient glacial deposits in Svalbard, high in the Arctic. These deposits, called tillites, are distinctive rocks, formed when glaciers grind over the landscape, picking up everything from fine clay to massive boulders, and eventually dropping them in a chaotic mixture when the ice melts. Tillites are unmistakable evidence of glaciation, and finding them in the Arctic was no surprise. But when Harland determined the age of these rocks, and reconstructed where Svalbard had been when they formed, he made a shocking discovery. These glacial deposits had formed when Svalbard was near the equator. At first, this seemed impossible. Glaciers at the equator would require a climate catastrophe beyond anything in recorded history. But as geologists looked more carefully at rocks of similar age around the world, they found the same story repeated again and again. In Australia, in Namibia, in China, in North America, wherever rocks from the period around 750 to 580 million years ago were preserved, they showed evidence of intense glaciation. And when the ancient positions of these continents were reconstructed using paleomagnetic data, many of them turned out to have been in tropical latitudes when the glaciers formed. The paleomagnetic evidence was particularly compelling. When volcanic rocks cool or when sediments settle in water, magnetic minerals within them align with Earth's magnetic field like tiny compass needles, recording both the direction to the magnetic pole and the inclination of the field lines. This inclination varies with latitude, steep near the poles and shallow near the equator, providing a record of where on Earth the rocks formed. Time after time, rocks showing clear evidence of glaciation also showed paleomagnetic signatures, indicating they had formed in tropical regions. The message seemed clear, however impossible it might seem that glaciers had once existed at the equator, which meant the entire planet must have been frozen. But how could such a thing happen? The key insight came from understanding the carbon cycle and its role in regulating Earth's climate. Carbon dioxide in the atmosphere acts as a greenhouse gas, trapping heat and warming the planet. This CO2 is constantly being removed from the atmosphere by chemical weathering of rocks, a process where rainwater, made slightly acidic by dissolved CO2, reacts with minerals to form carbonates that eventually wash into the ocean. Normally, this process is balanced by volcanic eruptions that return CO2 to the atmosphere, maintaining a relatively stable climate over geological time. The breakup of the supercontinent Rodinia, which we explored in our previous chapter, may have triggered a catastrophic disruption of this balance. As Rodinia fragmented, vast amounts of fresh volcanic rock were exposed to weathering in tropical latitudes where rainfall was abundant and temperatures were high, accelerating the chemical reactions that pull CO2 from the atmosphere. The placement of large land masses in the tropics was crucial because weathering proceeds much faster in warm, wet conditions than in cold or dry ones. With more land in the tropics than perhaps ever before or since, weathering would have gone into overdrive, stripping CO2 from the atmosphere faster than volcanoes could replace it. As CO2 levels dropped, the planet cooled. Ice sheets began to form at the poles, and because ice reflects sunlight back to space much more effectively than open water or land, the cooling accelerated The ice sheets grew, creeping toward the equator year by year, century by century. Climate models suggest that this process could have reached a tipping point when ice sheets extended to about 30 degrees latitude, roughly the position of modern-day Florida or Cairo. Once ice reached this critical latitude, the reflection of sunlight became so intense that runaway cooling ensued. Within perhaps just 1,000 years, a geological instant, the entire ocean surface could have frozen over, creating a Snowball Earth. Picture this frozen world in your mind. The oceans, which today cover more than 70% of Earth's surface with liquid water, were sealed beneath a layer of ice hundreds of meters thick. Near the equator, where today tropical fish swim in warm seas, the ice might have been thinner, perhaps only tens of meters, but still solid enough to walk on, to drive across, to build cities upon if any creatures capable of building had existed. The continents, what few of them poked above the ice, would have been buried under glaciers miles thick, grinding slowly across the landscape, pulverizing rocks into fine powder. The average global temperature during a Snowball Earth event would have been about -40 degrees Celsius, colder than modern Antarctica. The air would have been thin and dry with almost no water vapor to create clouds or precipitation. What little snow fell would have been fine and powdery, accumulating at a rate of perhaps just millimeters per year. The sky would have been a deep, dark blue, almost black at midday, with stars visible even during daylight hours. The sun, already dimmer than today because of its younger age, would have seemed even weaker, its light scattered and reflected by the global ice cover. Yet even in this frozen world, life persisted. This is one of the most remarkable aspects of the Snowball Earth theory. Somehow, despite the planet being locked in ice, life not only survived but continued to evolve. The evidence for this comes from molecular clocks, genetic analyses that suggest major evolutionary divergences occurred during the proposed Snowball Earth periods. But how could life survive such a catastrophe? The answer may lie in refugia, small pockets where liquid water persisted despite the global freeze. Volcanic hotspots would have created holes in the ice, like the polynyas that form in modern polar seas. Where glaciers met the sea, the grinding of ice against rock would have generated heat, potentially maintaining patches of open water. In the deep ocean, geothermal vents would have continued to spew hot, mineral-rich water, creating oases of warmth in the frozen darkness. And perhaps most importantly, the ice itself would have acted as an insulator, preventing the oceans from freezing solid all the way to the bottom. Life in these refugia would have been harsh and limited, but it would have been enough. Bacteria and archaea, the hardy microorganisms that had already survived billions of years of planetary changes, would have clustered around whatever energy sources they could find. Some would have lived on chemical energy from volcanic vents. Others might have survived in thin films of liquid water within the ice itself, or in pockets of brine that remained liquid even at extremely cold temperatures. And some photosynthetic organisms might have persisted in cracks in the ice, or in areas where the ice was thin enough for sunlight to penetrate. But if Earth became completely frozen, how did it ever thaw? This was one of the biggest challenges to the Snowball Earth hypothesis when it was first proposed. The answer lies in the fact that while ice had shut down the water cycle and chemical weathering, volcanoes continued to erupt. With no rainfall and no exposed liquid water, there was no way for chemical weathering to remove CO2 from the atmosphere. Volcanic CO2 would have accumulated slowly but steadily, building up to levels perhaps 350 times higher than today. It might have taken 10 million years or more, but eventually the greenhouse effect of all that CO2 would have become strong enough to overcome the reflectivity of the ice. When the melting began, it would have been catastrophic. Climate models suggest that once melting started at the equator, the entire global ice cover could have disappeared in just a few thousand years. The transition from icehouse to greenhouse would have been shocking in its speed and intensity. global temperatures would have swung from -40 degrees Celsius to +50 degrees Celsius, among the hottest conditions Earth has ever experienced. The melting of miles-thick ice sheets would have raised sea levels dramatically and rapidly, flooding vast areas of the continents. The aftermath of a Snowball Earth event would have been as dramatic as the freeze itself. With atmospheric CO2 at extreme levels and no ice left to reflect sunlight, the planet would have been plunged into an intense greenhouse climate. Torrential rains would have fallen as the water cycle roared back to life, possibly delivering decades' worth of modern precipitation in single storm events. These rains, acidified by the high CO2 levels, would have caused intense chemical weathering of the newly exposed rocks, delivering massive amounts of nutrients to the oceans. This is where the Snowball Earth theory connects directly to the Great Unconformity. The grinding of glaciers during the frozen period would have eroded vast amounts of rock from the continents. When the ice melted, this pulverized rock would have been exposed to intense chemical weathering in the greenhouse aftermath. Rivers swollen with meltwater would have carried enormous amounts of sediment to the sea. The combination of physical erosion during the glaciation and chemical erosion in its aftermath could account for the removal of billions of years' worth of rock record. The evidence for Snowball Earth events is written in distinctive rock sequences found around the world. These sequences typically begin with tillites, the glacial deposits we discussed earlier, often containing drop stones, rocks that fell from melting icebergs into otherwise fine-grained seafloor sediments. Above the tillites, we often find cap carbonates, distinctive limestone or dolostone layers that precipitated rapidly from seawater oversaturated with carbonate ions. These cap carbonates are thought to have formed in the greenhouse aftermath of Snowball Earth events, when intense weathering delivered huge amounts of dissolved minerals to the oceans. The cap carbonates themselves are remarkable rocks, unlike anything forming in today's oceans. They often display unusual textures and structures, including giant wave ripples, tube-like structures called tubestones, and layers of aragonite crystal fans that grew directly on the seafloor. These features suggest precipitation from seawater, with chemistry very different from modern oceans, consistent with the extreme conditions that would have followed a Snowball Earth event. The cap carbonates are typically just a few meters thick but represent perhaps thousands of years of continuous precipitation, a rain of minerals from oversaturated seawater. Above the cap carbonates, we often find evidence of the return to more normal conditions, with sandstones and shales recording the re-establishment of normal weathering and sedimentation patterns. But the world that emerged from Snowball Earth was not the same as the one that entered it. The intense erosion and weathering had delivered vast amounts of nutrients to the oceans, particularly phosphorus, which is essential for life but often limiting in marine environments. This nutrient pulse may have set the stage for the evolutionary innovations that followed. There's considerable debate about how many Snowball Earth events occurred and exactly when they happened. The strongest evidence is for two major glaciations, one around 750 to 700 million years ago called the Sturtian glaciation, and another around 660 to 635 million years ago called the Marinoan glaciation. Some scientists argue for additional events, both before and after these two, while others question whether the Earth was ever completely frozen, proposing instead a slush ball Earth with significant areas of open water. The timing of these proposed Snowball Earth events corresponds closely with the formation of the Great Unconformity in many locations. The glaciations would have occurred during the missing billion years, and their erosive power could explain why so little rock from this period survives. But the relationship is complex and not fully understood. In some places, the Great Unconformity seems to predate the Snowball Earth events, while in others, it postdates them. This temporal complexity suggests that while Snowball Earth may have contributed to the Great Unconformity, it might not be the sole explanation. The biological implications of Snowball Earth are profound. The extreme environmental pressures of global glaciation would have created an evolutionary bottleneck, killing off many lineages but potentially spurring innovation in the survivors. The isolation of populations in different refugia could have promoted divergent evolution, with different groups developing different solutions to survival in extreme conditions. When the ice melted and these populations mixed again, the genetic diversity generated during isolation could have fueled rapid evolution. Some scientists have proposed that Snowball Earth events were directly responsible for the evolution of complex multicellular life. The argument goes that the extreme conditions would have favoured organisms that could cooperate, with cells working together more effectively than they could alone. The high oxygen levels that might have built up under the ice, produced by photosynthesis but unable to escape to the atmosphere, could have provided the energy needed for larger, more complex organisms, and the nutrient pulse following deglaciation would have created ecological opportunities for these new forms of life to flourish. The evidence for increased biological complexity following Snowball Earth events is suggestive but not conclusive. Molecular clock studies suggest that major animal groups began diverging around the time of the proposed glaciations. Some of the earliest convincing fossils of complex multicellular organisms, including the enigmatic Ediacaran fauna, appear in rocks deposited shortly after the younger Snowball Earth event. But whether this timing is coincidental or causal remains debated. As we continue to contemplate this frozen world, it's worth considering what Snowball Earth would have looked like from space. Today, Earth is the blue planet, its oceans giving it a distinctive colour, visible from billions of miles away. But during a Snowball Earth event, our planet would have been white as Venus, but for completely different reasons. It would have been a world that looked dead, showing no obvious signs of the life huddled in refugia beneath the ice. An alien astronomer observing Earth during this time might have classified it as a frozen, lifeless world, never suspecting that it harboured the ancestors of all complex life we see today. The Snowball Earth hypothesis remains controversial, with active debate about almost every aspect of it. Some scientists question whether the paleomagnetic evidence for tropical glaciation is reliable, suggesting that the magnetic poles might have been in different positions than assumed, or that the rocks might have been remagnetized after formation. Others argue that the sedimentological evidence could be explained by local glaciation rather than global freezing. Still others question whether the Earth could have remained completely frozen for millions of years without life going extinct. Alternative models have been proposed to explain the evidence without invoking a completely frozen planet. The Slushball Earth model suggests that while ice covered much of the planet, a band of open water persisted at the equator. The high obliquity model proposes that Earth's axial tilt was much greater in the past, creating extreme seasons that could have allowed ice at the equator while maintaining open water elsewhere. The Jormungand model, named after the Norse world serpent, proposes that the ocean was covered by thin sea ice that could have been regularly broken up by tides and waves, allowing gas exchange with the atmosphere. Each of these models has its strengths and weaknesses, and the debate continues as new evidence emerges. Recent studies of the chemistry of cap carbonates have provided new insights into ocean conditions during and after the proposed glaciations. Analysis of ancient organic molecules has offered glimpses of what life was doing during these events, and improved climate models have helped scientists understand the conditions necessary to freeze and thaw the planet. But even as debate continues about the details, the broad picture that emerges is of a time of extreme climate change that fundamentally altered Earth's surface. Whether the planet froze completely or partially, whether there were two events or more, whether they lasted millions of years or tens of millions, the evidence points to glaciation on a scale never seen before or since. And this glaciation, however extensive it was, would have been a powerful agent of erosion, fully capable of contributing to the Great Unconformity. Moving beyond the ice, we must consider another powerful theory for the missing billion years, one that doesn't require the planet to freeze, but instead invokes the slow, steady, relentless power of erosion operating over vast spans of time. This is the theory of the Great Denudation, the idea that the assembly and breakup of supercontinents created conditions that accelerated erosion to unprecedented levels. It's a less dramatic story than Snowball Earth, but no less profound in its implications. The key to understanding this theory lies in recognizing how the configuration of continents affects erosion rates. When continents collide to form supercontinents, massive mountain ranges rise along the collision zones. These mountains are immediately attacked by erosion, with rivers carrying sediment from the peaks to the sea. But in a supercontinent, many of these rivers must travel vast distances through the continental interior before reaching the ocean. Along the way, much of their sediment is deposited in inland basins, temporarily stored rather than delivered to the deep ocean where it might be preserved. During Rodinea's existence, the supercontinent's interior would have been a vast depositional basin, collecting sediment from the surrounding mountains. But these interior sediments would have been vulnerable to later erosion. When Rodinia broke apart, new rivers would have cut through these deposits, carrying them to the newly formed ocean basins. The breakup would have rejuvenated erosion, with steep gradients from the Rift Mountains to the new seas driving rapid down-cutting. The process of continental breakup itself generates conditions favourable for intense erosion. The rifting process creates steep escarpments that retreat inland through erosion, stripping away older rocks. The volcanic activity associated with rifting brings deep, easily weathered rocks to the surface. The opening of new ocean basins changes climate patterns, potentially bringing more rainfall to previously dry regions. All of these factors would have accelerated erosion during and after Rodinea's fragmentation. But perhaps the most important factor in the Great Denudation theory is simply time. The period between Rodinea's assembly and the Cambrian explosion spans several 100 million years, an almost incomprehensible duration even by geological standards. Given enough time, even modest erosion rates can remove vast amounts of rock. An erosion rate of just 1 millimeter per 1,000 years, barely measurable on human timescales, would remove a kilometer of rock in 1 billion years. The missing time of the Great Unconformity represents enough time for normal erosion to remove several kilometers of rock from the continents. The evidence for extensive erosion during this period comes from several sources. Studies of ancient river deposits show that many Precambrian rivers were braided systems carrying enormous amounts of sediment, suggesting rapid erosion of their source areas. The chemistry of ancient oceans, preserved in limestone and other marine rocks, shows pulses of increased nutrient delivery that would be consistent with periods of enhanced continental erosion. And the thermochronology of rocks that survived this period, which records their cooling history as they were exhumed by erosion, suggests kilometers of rock were removed from many areas. The Great Denudation theory also helps explain some puzzling features of the Great Unconformity that are difficult to account for with the Snowball Earth hypothesis alone. For instance, the unconformity is time transgressive, meaning it formed at different times in different places. This is exactly what we would expect from erosion related to continental breakup, as different parts of the supercontinent would have rifted at different times. The theory also explains why some fragments of the missing time period are preserved, as these would represent areas that escape the most intense erosion, perhaps because they were in stable continental interiors or areas of subsidence rather than uplift. One of the most compelling aspects of the Great Denudation theory is that it doesn't require any unusual or catastrophic events. It simply requires the normal processes of plate tectonics and erosion, operating over extremely long time periods. Mountains rise and are worn down. Continents assemble and break apart. Rivers carry sediment to the sea. These are processes we can observe today, just operating over timescales that dwarf human experience. In this view, the Great Unconformity is not a mystery requiring a special explanation, but simply the expected result of Earth's normal geological processes given sufficient time. Yet there are problems with the Great Denudation theory as well. The unconformity is remarkably flat in many locations, extending for hundreds of miles with barely any relief, Normal erosion typically creates irregular surfaces, following variations in rock hardness and structure. To create such flat surfaces would seem to require something more than normal erosion, perhaps a combination of erosion and marine planation, as sea levels rose and fell. Additionally, the global nature of the unconformity suggests that whatever caused it affected most or all continents simultaneously, which is difficult to explain through normal erosion alone. This brings us to a third major theory, one that combines elements of both Snowball Earth and the Great Denudation, while adding a biological component. This is the idea that life itself played a crucial role in creating the Great Unconformity. It's a theory that recognizes life not as a passive passenger on Earth's geological journey, but as an active participant in shaping the planet's surface and chemistry. The story begins with the evolution of new forms of life during the Precambrian, particularly organisms that could burrow into sediment or bore into rock. The first evidence of bioturbation, the mixing of sediment by burrowing organisms, appears in the geological record around the same time as the Great Unconformity. These early burrowers would have fundamentally changed how sediments behaved, making them more susceptible to erosion. Sediments that had been bound by bacterial mats for billions of years were suddenly being churned and loosened, making them easier for currents and waves to transport. Even more significant might have been the evolution of organisms that could bore into rock itself. Modern organisms, like certain sponges, mollusks, and worms, can drill holes into solid rock, weakening it and making it more susceptible to erosion. If such organisms evolved during the late Precambrian, they could have dramatically accelerated the breakdown of coastal rocks, contributing to the erosion that created the Great Unconformity. But the biological contribution to the Great Unconformity might extend beyond simple physical effects. The evolution of new metabolic pathways could have changed ocean chemistry in ways that accelerated rock weathering. For instance, the production of organic acids by early organisms could have lowered the pH of seawater, making it more corrosive to rocks. The evolution of biomineralization, the ability to precipitate minerals like calcium carbonate, would have changed how elements cycled through the ocean atmosphere system, potentially affecting global climate and weathering rates. The timing of major biological innovations corresponds intriguingly with the formation of the Great Unconformity. Molecular clock studies suggest that animals began diversifying around 800 to 700 million years ago, right in the middle of the missing time. The first convincing fossils of complex multicellular organisms appear shortly after the Unconformity. This temporal correlation might not be coincidental. Perhaps the biological innovations that would eventually lead to the Cambrian explosion also contributed to the erosion that created the Great Unconformity. There's also the possibility that the relationship worked in reverse, that the erosion associated with the Great Unconformity created conditions that spurred biological evolution. The massive delivery of nutrients to the oceans would have fertilized marine ecosystems, potentially triggering blooms of photosynthetic organisms. These blooms would have produced oxygen, creating new ecological niches for organisms that could use oxygen for metabolism. The increased productivity might have provided the energy necessary for the evolution of larger, more complex organisms. The interplay between geological and biological processes during this period would have been complex and mutually reinforcing. Erosion delivered nutrients that fueled biological productivity. Biological innovations changed how sediments and rocks behaved, affecting erosion rates. Climate changes driven by continental configuration affected both erosion and evolution. It was a time when Earth's geological, chemical, and biological systems were all in flux, interacting in ways that transformed the planet. As we contemplate these various theories for the Great Unconformity, it's important to recognize that they're not mutually exclusive. The truth likely involves elements of all of them. Snowball Earth events might have occurred, contributing massive erosion during some periods. The breakup of Rodinia would have accelerated erosion through normal geological processes. Biological evolution would have changed how rocks and sediments behaved. The Great Unconformity might not have a single cause, but rather represent the cumulative effect of multiple processes, all operating during a crucial period in Earth's history. This multi-causal view of the Great Unconformity is gaining support as more evidence accumulates. Different regions show different patterns that might reflect the dominance of different processes. Some areas show clear evidence of glacial erosion, while others seem more affected by chemical weathering. Some locations preserve evidence of biological activity, while others seem purely geological. The global unconformity might be a patchwork of local and regional erosion events that happen to occur during the same general period of Earth's history. The search for answers continues with new technologies and approaches. Geochemists are developing increasingly sophisticated ways to trace the sources and sinks of elements during this period. Paleontologists are finding and describing new fossils that fill in gaps in the evolutionary record. Climate modelers are creating ever more detailed simulations of Precambrian climate. And field geologists continue to discover new exposures of the Great Unconformity, each one potentially holding clues to the mystery. One particularly promising avenue of research involves the study of detrital zircons, tiny crystals of zirconium silicate that are nearly indestructible. These crystals can survive multiple cycles of erosion and redeposition, carrying information about their source rocks even after those rocks have been completely destroyed. By analysing the ages and chemistry of detrital zircons in sediments deposited after the Great Unconformity, scientists can learn about the rocks that were eroded to create it. This work has revealed that vast amounts of continental crust were indeed destroyed during the formation of the Unconformity, supporting the idea of extensive erosion. Another important approach involves studying modern analogues for the processes that might have created the Great Unconformity. Scientists study erosion rates in different tectonic and climatic settings today, trying to understand what conditions lead to the most rapid landscape denudation. They examine how modern ice sheets erode the landscape, looking for insights into how Snowball Earth glaciers might have behaved. They investigate how life affects erosion and weathering in modern environments, from the breakdown of rocks by lichens to the bioturbation of sediments by worms. But perhaps the most profound insights come from stepping back and viewing the Great Unconformity in the context of Earth's entire history. Our planet has been recording its history in stone for over 4 billion years, yet the rock record is full of gaps. The Great Unconformity is the largest and most dramatic of these gaps, but it's far from the only one. Every unconformity represents lost time, lost information, lost history. The Earth's geological record is not a complete autobiography, but a fragmentary memoir, with some chapters detailed and others missing entirely. This fragmentary nature of the geological record has profound implications for how we understand Earth's history. We must always remember that we're working with incomplete information, that there might be major events and processes in Earth's past that left no record at all. The history we reconstruct from the rocks is biased toward processes that preserve rocks rather than destroy them. Periods of intense erosion, like whatever created the Great Unconformity, are paradoxically the hardest to study because they destroy the evidence of their own existence. Yet even with these limitations, the geological record tells an amazing story. From the fragments that survive, we can piece together a narrative of a planet that has undergone incredible transformations. We can trace the evolution of life from simple bacteria to complex ecosystems. We can reconstruct the dance of continents across the globe. We can infer changes in climate and ocean chemistry. And we can identify mysteries like the Great Unconformity that remind us how much we still have to learn. The Great Unconformity also has lessons for the present and future. It shows us that Earth is capable of changes far beyond anything in human experience. It demonstrates that processes operating slowly over millions of years can have effects as dramatic as any catastrophe. It reminds us that the current configuration of continents and oceans, the current climate, the current biosphere, are all temporary, destined to change dramatically given enough time. As we near the end of our exploration of the Great Unconformity, it's worth returning to the human perspective on this vast mystery. When we place our hand on an exposure of the unconformity, we're touching a boundary that represents a third of Earth's history compressed into a line. Below our hand are rocks from deep time, from an Earth so different it might as well be an alien planet. Above are rocks from a more familiar world, though still ancient beyond easy comprehension. And between them, invisible but profound, is an absence that speaks louder than any presence could. The mystery of the missing billion years connects us to the deep history of our planet in a visceral way. It's one thing to read about geological time in textbooks, to memorize dates and periods and events. It's another thing entirely to stand before the physical evidence of a billion missing years, to see with your own eyes the place where Earth's memory fails. The Great Unconformity makes deep time tangible, transforming an abstract concept into something you can touch, something you can photograph, something you can stand on. For geologists, the Great Unconformity is both a frustration and an inspiration. It's frustrating because it represents so much lost information, so many questions that might never be answered. What organisms lived during the missing time? What climates prevailed? What mountains rose and fell? What oceans opened and closed? These questions haunt us because we know the answers once existed, written in rocks that are now gone forever. But the Great Unconformity is also inspiring because it represents one of the great remaining mysteries in Earth science. In an age when it might seem like all the big questions have been answered, here's proof that fundamental mysteries remain. The Great Unconformity challenges us to be creative in our approaches, to develop new techniques, to think in new ways about how planets evolve. It's a puzzle that has engaged some of the brightest minds in geology for over a century, yet it remains unsolved. The study of the Great Unconformity also illustrates how science progresses. The early geologists who first recognized the unconformity could only describe it and wonder at its meaning. As new technologies developed, from radiometric dating to paleomagnetism to geochemistry, each generation of scientists has been able to ask new questions and propose new answers. The Snowball Earth hypothesis would have been impossible without paleomagnetic data. The Great Denudation theory required understanding of plate tectonics. The biological theories needed knowledge of Precambrian life that has only recently become available. Today's scientists studying the Great Unconformity have tools and knowledge that would have seemed miraculous to earlier generations. They can date rocks to within a few million years of their formation. They can reconstruct ancient climates from the chemistry of minerals. They can trace the evolution of life through molecular clocks. They can model the entire Earth system with supercomputers. Yet even with all these advances, the mystery persists, reminding us that nature still holds secrets that all our technology cannot unlock. Looking forward, what might future generations discover about the Great Unconformity? Perhaps new dating techniques will allow us to precisely determine when the unconformity formed in different locations, revealing patterns we cannot yet see. Perhaps fossils from the missing interval will be discovered, preserved in some unexpected way, telling us about life during the gap. Perhaps climate models will become sophisticated enough to definitively test whether Snowball Earth could have occurred. Perhaps entirely new theories will emerge, based on discoveries we cannot yet imagine. Or perhaps the Great Unconformity will remain a mystery, a permanent reminder of the limits of scientific knowledge. There's something beautiful about the idea that Earth might keep some of its secrets forever, that not every question has an answer we can reach. The missing billion years might remain missing, a gap in our planet's story that we must simply accept. This would not be a failure of science, but a recognition of the vastness of deep time and the power of geological processes to erase their own history. As we contemplate the various theories we've explored, from Snowball Earth to the Great Denudation to biological causes, it's clear that each offers valuable insights even if none provides a complete explanation. The truth likely involves all of these processes and perhaps others we haven't yet considered. The Great Unconformity might not have a single cause, but rather be the result of a perfect storm of geological, climatic, and biological factors, all operating during a critical period of Earth's history. This complexity is itself a lesson. We humans like simple stories with clear causes and effects, but nature rarely obliges. The real world is messy and multi-causal, with feedback loops and emergent properties that can produce outcomes no one could predict. The Great Unconformity reminds us that Earth is a complex system where geology, climate, chemistry, and biology all interact in intricate ways. Understanding any one part requires understanding the whole, yet the whole is almost impossibly complex. The Great Unconformity also connects to larger questions about the nature of time and memory. How does a planet remember its history? What determines which events leave permanent records and which are erased? Earth's memory is selective, preserving some moments in exquisite detail while completely forgetting others. The fossils of the Burgess Shale preserve soft tissues from 508 million years ago, yet entire mountain ranges from the missing billion years have vanished without a trace. This selectivity shapes our understanding of the past, creating a narrative with some chapters vivid and others blank. In a sense, we're all products of the Great Unconformity. The events that created it, whatever they were, set the stage for the Cambrian explosion and all that followed. The nutrients delivered to the oceans by the massive erosion fertilized the evolutionary innovations that led to complex animals. The changes in ocean chemistry created new ecological niches. The clearing away of old rocks made room for new sediments to accumulate, preserving the fossil record of emerging life. Without the Great Unconformity, the history of life might have been very different. This brings us to perhaps the most profound aspect of the Great Unconformity, its role in the story of consciousness itself. The missing billion years preceded the evolution of complex nervous systems, of eyes and brains, of the ability to perceive and think about the world. In erasing so much of Earth's history, the forces that created the Great Unconformity also cleared the stage for the emergence of minds capable of wondering about that erasure. We conscious beings, products of the evolution that followed the unconformity, now look back and puzzle over the gap that preceded our origins. There's a deep irony in this. The same processes that erased a billion years of history also created the conditions for beings who would someday try to recover that history. We are detectives investigating the destruction of evidence that occurred before detectives were possible. We use our consciousness, which exists only because of the events after the unconformity, to try to understand what happened before and during it. It's like a book trying to read the pages that were torn out before it was written. This recursive quality of studying the Great Unconformity, where the products of an event investigate the event itself, is characteristic of much of deep time geology. We use the present to understand the past, even though the past created the present. We assume that physical laws have remained constant, that processes we observe today also operated in the past, even though we know Earth has changed dramatically over time. These assumptions, collectively known as uniformitarianism, are necessary for geological science. Yet the Great Unconformity reminds us that the past might have been more different than we imagine. As our exploration of the Great Unconformity draws toward its close, it's worth considering what this mystery means for our understanding of other planets. Mars, Venus, Mercury, the Moon, all have their own geological records with their own gaps and unconformities. The processes that erased a billion years of Earth's history might have analogues on other worlds, or those worlds might have experienced entirely different types of erasure. As we explore the solar system and eventually planets around other stars, we'll need to remember the lesson of the Great Unconformity, that planetary histories are incomplete, that absence of evidence is not evidence of absence. The search for life on other worlds is particularly affected by this lesson. If Earth can lose a billion years of its history, what might other planets have lost? Could Mars have hosted life during periods now erased from its geological record? Could Venus have been habitable before its surface was completely resurfaced by volcanism? The Great Unconformity teaches us to be humble about what we think we know about planetary histories, to always consider what might be missing from the record. Even on Earth, there might be other great unconformities waiting to be discovered, gaps in the record that we haven't yet recognized. The deep ocean floor, constantly recycled by plate tectonics, preserves at most 200 million years of history. The continental crust, though older, is full of gaps and unconformities at various scales. Every outcrop of rock represents a tiny fragment of Earth's history, surrounded by temporal darkness. We see the past through windows, but most of the wall is opaque. Yet despite all these limitations, despite the missing billion years and all the other gaps in the record, we've managed to reconstruct a remarkably detailed history of our planet. We know about supercontinents that assembled and broke apart. We know about ice ages and greenhouse periods. We know about mass extinctions and evolutionary radiations. We know about the gradual oxygenation of the atmosphere and the changes in ocean chemistry. This knowledge, painstakingly assembled from fragments and clues, represents one of humanity's greatest intellectual achievements. The Great Unconformity stands as both a triumph and a challenge for this intellectual endeavour. It's a triumph because we've recognized it, dated it, and developed plausible theories to explain it, all from the absence of evidence rather than its presence. It's a challenge because it remains unsolved, a mystery that has resisted over a century of scientific investigation. It reminds us that there's still so much to learn about our planet, still so many secrets hidden in the rocks or erased from them. As you drift towards sleep, contemplating the vastness of the missing billion years, consider how this mystery connects you to the deep history of Earth. The atoms in your body, forged in stars and processed through countless cycles of rock and life, might once have been part of mountains that were erased during the Great Unconformity. The calcium in your bones might have dissolved from rocks being weathered during the missing time. The iron in your blood might have precipitated from ancient seas during Snowball Earth events. You're connected to this mystery not just intellectually but physically, your very substance having participated in the events we've been exploring. The story of the Great Unconformity is far from over. Somewhere, perhaps in a remote desert or on an inaccessible mountain peak, there might be rocks that preserve parts of the missing time waiting to be discovered. Somewhere in a laboratory, a scientist might be developing a new technique that will unlock secrets hidden in the minerals that survived the Great Erasure. Somewhere in a computer, a model might be running that will finally explain how a billion years of history could vanish so completely. Or perhaps the mystery will deepen. New evidence might contradict current theories, forcing us to reconsider everything we think we know. The Great Unconformity might turn out to be even more complex than we imagine, involving processes we haven't yet conceived. This is the nature of science, always provisional, always ready to be revised, in light of new evidence. The theories we've explored tonight might someday seem quaint, like early ideas about the Earth being hollow or the oceans being connected to underground reservoirs. But whatever future discoveries reveal, the Great Unconformity will remain one of the most profound features of Earth's history. It represents a boundary between worlds, between the alien Earth of the deep Precambrian and the more familiar Earth that followed. It marks a transition from a planet dominated by microbes to one where animals would soon flourish. It separates an old Earth from a younger Earth, though both are ancient beyond easy human comprehension. The rocks that border the Great Unconformity have been patient witnesses to Earth's transformation. The ancient basement rocks below have endured billions of years, surviving the erasure that claimed their younger companions. The sedimentary rocks above record the recovery, the return of deposition, and the explosion of life. Between them lies the silence of the missing time, a gap that speaks eloquently about the power of geological processes and the fragility of planetary memory. As we prepare to conclude our journey through Earth's missing billion years, it's worth reflecting on what this mystery teaches us about the nature of scientific inquiry. The Great Unconformity shows us that some of the most important scientific questions arise from what's absent rather than what's present. It demonstrates that patient observation and creative thinking can extract information from even the most recalcitrant evidence. It reminds us that science is a collective endeavour, with each generation building on the work of those before. The scientists who study the Great Unconformity are detectives of deep time, using every tool at their disposal to investigate a case where most of the evidence has been destroyed. They must be creative, persistent, and comfortable with uncertainty. They must be willing to propose bold hypotheses while remaining ready to abandon them if the evidence demands. They must think across disciplines, combining insights from geology, chemistry, physics, biology, and even astronomy to understand what happened during Earth's missing billion years. This interdisciplinary nature of studying the Great Unconformity reflects a broader trend in Earth science. The old boundaries between different fields are breaking down as scientists recognize that Earth is a single, integrated system. The atmosphere affects the oceans, which affect the continents, which affect life, which affects everything else. Understanding any part requires understanding the whole. The Great Unconformity, touching as it does on geology, climate, chemistry, and biology, exemplifies this holistic approach to understanding our planet. The mystery also highlights the importance of fieldwork in Earth science. While laboratory analyses and computer models are invaluable, there's no substitute for standing at an outcrop, hammer in hand, observing the rocks directly. Every exposure of the Great Unconformity is unique, potentially holding clues that exist nowhere else. The geologists who trek to remote locations to study these outcrops are the frontline investigators of this ancient mystery, gathering the raw data that all other studies depend on. But the Great Unconformity is more than just a scientific puzzle. It's a reminder of our place in the cosmos, a humbling demonstration of the vastness of time and the power of planetary processes. When we contemplate the missing billion years, we're forced to confront the insignificance of human timescales compared to geological ones. Entire civilizations could rise and fall in the time it takes for a mountain to erode by a millimeter. The span of human history is less than a rounding error in the age of the Great Unconformity. Yet paradoxically, this vast mystery also demonstrates the power of human intellect. Despite the enormous gulf of time that separates us from the events that created the Great Unconformity, we can still investigate them, still develop theories about them, still work toward understanding them. We can use the laws of physics and chemistry, which we assume have remained constant, to interpret evidence from a time before complex life existed. We can use our consciousness, evolved so recently, to probe events from the deep past. This ability to transcend our immediate experience through science is one of humanity's most remarkable capabilities. We are ephemeral beings, living for mere decades, yet we can study processes that operate over billions of years. We're confined to a single planet, yet we can understand our place in the cosmos. We are products of evolution, yet we can trace our origins back through deep time. The Great Unconformity challenges this ability, pushing us to the limits of what we can know about our planet's past. As you continue to drift towards sleep, let the vastness of the missing billion years wash over you like a gentle tide. Feel yourself floating in deep time, suspended between the ancient basement rocks and the younger sediments above. The boundary between them, thin as paper yet representing eons, passes through your consciousness like a whisper from the deep past. You are connected to this mystery through every atom of your being, through the long chain of cause and effect that links the Great Unconformity to your existence here and now. The earth beneath you has forgotten a billion years of its history, yet it remembers enough to tell the story of life's emergence and flourishing. The rocks have been patient teachers, waiting through the ages for conscious beings to evolve who could read their stories, And now, here you are, a collection of atoms temporarily organized into consciousness, contemplating the very forces that made your existence possible. The Great Unconformity is part of your story, even if that part is a mystery, a gap, an absence that defines the presence that followed.